Yeah? Does anyone have any strategy to suggest? From negation alpha, I want to get beta as well as not beta. Has anyone thought of using not alpha as beta? What does that mean? From not alpha, I want beta as well as negation beta. Well, beta, if I choose not alpha as beta, not alpha implies not alpha, right? We have just proved this. We have proved alpha implies alpha for any formula. So not alpha implies not alpha. And I'll also want not alpha implies not alpha. How do I hope to get that? Remember, we have something on the left hand side. When you have something on the left hand side, how do I bring it out to the right? Deduction theorem. Do you see that? From the left hand side, if I get double negation alpha, I can get double negation alpha implies, anything implies double negation alpha. In particular, not alpha implies double negation, right? Which is what I need. So in the presence of double negation alpha, I can always say not alpha implies not alpha. And not alpha implies not alpha is there. So that means from not alpha, I can get a contradiction. Therefore, I can derive. That's the proof idea. And that's the proof. First, from not alpha implies not alpha is an axiom, right? This is just axiom 1, where I have substituted not alpha, right? Not alpha already holds, implies not, anything implies it, in particular not alpha. By deduction theorem, therefore, I can push it to the left. So in the presence of not alpha implies not alpha. Now, not alpha implies not alpha. This is something we just proved, right? 10 minutes ago or 5 minutes ago, right? Therefore, under this assumption also not alpha implies not alpha. Now from not alpha, I got not beta and I've got beta. Apply a reductio ad absurdum, therefore from not alpha. Please take a look at it and check that the steps are okay. Make sure you've understood that. Yeah. Any questions? I mean, really, the only reasonable question is how the hell do you come up with this substitution, right? How do you think of? Yeah. I mean, that's really the only serious thing in this, because the moment you see it, somebody tells you that it's obvious, right? The proof. See, this is the fundamental problem. Somebody presents a proof, verifying that the proof is correct is very simple. Coming up with the proof is hard. Well, one of the basic lessons in this whole thing with Boolean formulas. Yeah. Now we are actually doing proofs of tautologies, right? These, not alpha implies alpha is a valid formula, and we are trying to do it. Right? As I said, from all this experience, we want to come up with a general technique for taking any tautology and doing it. Okay, but we are still somewhere far away from all. What about this? The other double negation. Alpha implies not alpha. Please try. And notice that this is not as simple, right? Why? Because in the former one, the axiom 3 suggested alpha. So alpha was in the right hand side of the implication. And that's what is there in the axiom. But now I've got a double negation sitting here. So how do I go about it? Once again, please try. The I Let me suggest to you that the experience of what I just did now, not alpha implies alpha. Try. It's same thing. Something like that has to be done. Any ideas? Is there a proof strategy? Again, which axiom is the principal thing you were trying? What about people in the darkness? Jenny, Aditya, any strategies? Okay, once again, axiom 3 is the only hope, right? But then, yeah, so axiom 3 is all that we can use. But then what must we, remember we want to derive double negation alpha. So what must we start with and prove a contradiction? Yes, Ananya? What should I start with and get a contradiction so that I can derive double negation alpha? Remember, if I want to get beta, I have to start with not beta and get a contradiction, right? So if I want not alpha,
Not of not alpha.
triple negation alpha, absolutely. So you must start with triple not alpha and get a contradiction. And what is available to us on the left hand side? Alpha. Okay, that's good news. From alpha, triple not alpha will also imply alpha. So that's not a problem. So if I want to get a contradiction, what I want is triple not alpha should imply alpha, which is okay. But triple not alpha should also imply not alpha. Will triple not alpha imply not alpha? Single not alpha? Yes, Siddharth?
Yes, sir, we just proved that not
We
not
just
alpha
proved
implies
it.
alpha.
We just proved it. That's it. Huh? That's it. You're done. Okay. So I don't know what you're trying on. See, this is uh, one problem with online, right? I have no idea what you're trying. right? In a physical classroom, it's nice to walk around, see what you're trying, and say, okay, this is the sort of thing you should try, and this is, what formulas are you trying. If I see, I can help, right? Now, so I don't know what formulas you're trying. The best way is to always start from the end. This is what I want to prove, right? Double knot alpha is what I want to prove. So I must make an assumption triple knot alpha. I mean, there's no choice left there. And the thing is, I must get a contradiction, right? I must get a beta as well as negation beta. Well, I must use the assumption. The assumption is innocuous. It says alpha. So a good choice for beta is alpha. But then I need a negation alpha, right? But then I notice that triple knot alpha implies knot alpha comes from the previous one. So we first proved alpha implies alpha. Use that in the proof of double knot alpha implies alpha. And we are using that in the proof of alpha implies knot knot, right? So there is a progression. Of course, I'm setting it up for that reason. Right? This is not innocent at all. So, yeah. So this is what I have written. So we do need to assume triple knot alpha and get a contradiction, and we can do that. Well, alpha implies triple knot alpha implies alpha, but that is by axiom. By deduction theorem, I can push it to the left-hand side. So I get triple knot alpha implies alpha. Triple knot alpha implies knot alpha is our previous proof, right? I've just substituted, right, knot alpha here for the original. Now, therefore, I can have an assumption alpha here, and for triple knot alpha, I get alpha as well as knot alpha. Apply reduction ad absurdum, and you get double knot alpha. Okay, so this tells me alpha implies double knot alpha. Okay, now comes the next. Any guess for what is the next thing that I'm going to ask you to prove? There is a method in this madness, right? Okay. The other double negation. Okay. No, the other RAA. RAA is of this form, right? Not alpha implies not beta, and not alpha implies beta gets you alpha. You assume not alpha, get a contradiction to get alpha. What if I start with alpha and get a contradiction to get not alpha? That means I'm looking for a form. Alpha implies not beta, implies. Alpha implies beta, implies not alpha. Now, this is certainly valid. So there should be a derivation. Can you please derive that? Is the formula clear? It's exactly the same as RAA, except that you're starting with alpha. Alpha implies not beta implies. Alpha implies beta implies to the right, not alpha. Once again, think about what we are trying to do. We want to get not alpha to the right. So what is the form in which the existing RAA can be used? I must have double knot alpha, right? From double knot alpha implies not beta, double knot alpha implies beta, I want a contradiction. But I am already allowed to see alpha implies not beta and alpha implies beta is given to me. Somehow from alpha implies not beta, I want to get to double knot alpha implies not beta. From alpha implies beta, I want to get to double knot alpha implies beta. Does that seem feasible? Of course it is, because we have already shown not alpha implies alpha. Put the two together, right? Here you're allowed an assumption alpha implies not beta, right? So, and we already know not alpha implies alpha. Put the two together and get not alpha implies not beta. This allows you an assumption alpha implies beta. Right? Put not alpha implies alpha and get a not alpha implies beta. From not alpha, I get both. Now, how do I make these into assumptions? There is a long formula. Well, deduction theorem. Deduction theorem will let you push it all to the left, use it as assumptions, and this is all there is. So, alpha, oh, I'm sorry. Yeah. First, yeah. Well, I have proceeded by using alpha implies not alpha. Now, we have RA in both forms, right? Reductio ad absurdum axiom, and then the theorem that we have got. And now I can use it to remember one of the steps that we had last time was showing that if gamma is consistent, then for every formula, either gamma union negation alpha is consistent or gamma union alpha is consistent. That is, if you have a consistent set, take any formula, either you can add alpha consistently or its negation consistently, right? And where did we use this step? In the Lindenbaum construction. Given a consistent set, to extend it to a consistent and complete set, we enumerate the formulas, look at a formula alpha k in turn, and then decide whether to add it or not. And in the final proof, we argued that the whole set is complete because either the formula alpha would have got added or negation alpha. And this is a crucial lemma. And I did mention this as one of the things. Now, how do I prove that? Here is a proof. Suppose not. That means what? Gamma union negation alpha is inconsistent. Gamma union alpha is inconsistent. By definition of inconsistent, what does it mean? I can get a contradiction. From gamma union negation alpha, I can derive a little gamma as well as I can derive a negation gamma. Gamma union alpha is inconsistent. So I can derive delta as well as not delta. Right? Now, from the gamma proofs, use RAA and you will get alpha. Do you see this? Because I will get pushing this not alpha implies gamma, not alpha implies not gamma. Exactly like we did all these RAA proofs. So I'll get alpha. What about here? From the delta proofs, I'll get alpha implies delta, alpha implies not delta. And now the second form of RAA, I can get not alpha. So I get gamma derives alpha, gamma derives negation alpha, so gamma is inconsistent, contradicting our assumptions. That's why, after all, I proved this, the second form of RAA also. Yeah. This is a, once again, see how the proof works. Start with gamma is consistent. We want to show that for any formula, either you can add that formula consistently or negation alpha consistently. Suppose you cannot, right? Then there is some alpha such that both these sets are inconsistent. From the inconsistency of the first set, you get two proofs, one with gamma and one with negation gamma. From the inconsistency of the second set, you get two proofs, delta and non-delta, for some gamma and delta. Now from these, use the deduction theorem to push the not alpha to the left, to the right. So you will get gamma derives not alpha implies not gamma. And you will get gamma derives not alpha implies gamma. Now use the RAA axiom and modus ponens twice. And you will be able to show that gamma derives alpha. Because you assume negation alpha and you got a contradiction. Right? Now symmetrically here, from this you will get alpha implies not delta. From this you will get alpha implies delta. And we have already shown that the other form of RAA is also valid. It's derivable, and you get gamma. Putting these two together, you get a contradiction that gamma is consistent. So, yeah, I mean, this is really straightforward. And this is why. And now, there is another crucial step in the inductive step in the truth lemma. What was that? We needed to show that in the model, a formula is true if and only if it is in the consistent and complete set. So that involves closure property. So if gamma is a consistent and complete set, there's delta there, then for any formulas alpha beta, the implication alpha implies beta belongs to gamma if and only if either alpha is not there or beta is there. This is a closure property if I prove. Of course, this basically says by induction hypothesis in the model alpha is not true or beta is true. That means alpha implies beta is true in the model. So that's it. So this is all we need to. How do you prove this for a consistent and complete set? Well, first, suppose alpha implies beta belongs to gamma. Now, if alpha does not belong to gamma, we are through. Right? Otherwise, alpha belongs to gamma. Now, alpha implies beta belongs to gamma and alpha belongs to gamma. That means gamma derives alpha implies beta, gamma derives alpha. Therefore, by modus ponens, gamma derives beta, but it's a complete set. So beta better belong to gamma. Right? Why? Suppose beta doesn't belong to gamma. What will happen? Negation beta will belong to gamma. Gamma derives beta is what's up. We saw gamma derives negation beta. That's a contradiction. Gamma is consistent. So if it's consistent and complete, if gamma derives beta, beta better belong to gamma. This is the left to right direction. What about right to left? Well, assume that there are two cases here. In each of the cases, we have to show that alpha implies beta belongs to gamma. Well, suppose beta belongs to gamma. Gamma derives beta, and by axiom, beta implies alpha implies beta. Right? So gamma derives beta and gamma derives this. Therefore, by modus ponens, gamma derives alpha implies beta. And by the same logic, like I said, for a consistent and complete set, if that set derives something, it must belong to it. Right? Completeness is very critical. Do you understand this property? If it's consistent and complete, right? If gamma derives delta, delta must belong to gamma. Otherwise, why? Negation delta will belong to gamma, and I'll get a proof of not delta from gamma. I already know that gamma derives delta. If gamma derives negation delta, it will contradict the consistency. So, what about the other case? Suppose alpha does not belong to gamma. By completeness, not alpha belongs to gamma. Now, since from negation alpha, alpha I can derive beta. I remember we went through this. By deduction theorem, not alpha derives alpha implies beta. Right? But then not alpha belongs to gamma. So gamma derives not alpha. Therefore, gamma derives alpha implies beta. Yeah, done. Yeah. So, I mean, again, gamma derives alpha implies beta means alpha implies beta belongs to it. So, even those two steps that we had in the proof of the truth lemma, they are also true. So, I'm saying that last time I said, okay, these things can be proved and went on, but here we established actually these proofs and used the proofs to complete the proof of the completeness. And so you see that these are but a few examples. In general, finding proofs involves a great deal of ingenuity. And most importantly, it's very hard to see, looking at the formula, which formulas have short proofs, right? Because we saw that something like alpha implies not alpha forced us to look at some substitution, right? I mean, alpha implies alpha, right? The substitution we had to use was a much longer form, right? And it actually grows as something bigger before it gets shorter, right? So in general, the space complexity of deductions is quite non-trivial. In fact, it's one of the very, very interesting things about propositional logic, There is a lot of stuff about P and P and so on. And after all, Boolean satisfiability is what started the whole theory of NP completeness. But that's what you call the time complexity. The space complexity is about I need space to write down my formulas. Right? Forget about gamma. Take tautologies. Right? Look at the tautologies that we looked at. Alpha implies alpha. Not alpha implies alpha. Alpha implies not. Alpha implies not beta, implies alpha, implies beta, implies not. Things of this kind. These are all tautologies. Now, the intermediate steps that I'm talking about are where you write down, right? So, the notion of space complexity is about how much I need to write down, right? If I can look at the formula and say, hey, what have we got? I've got only implication and negation, right? If there has got, you know, two implications in the formula that I'm beginning with, maybe I should use 5 implications. If you can get something like that, you should be able to control this. And what I'm pointing out is that this is bloody non-trivial. Okay, so this turns out to be a very important topic in the area. We're not going to talk about complexity much here at all, but this is the thing that you're going to learn hopefully a lot of if you're learning theoretical computer science. Complexity of Boolean formulas is going to go with you all your life pretty much, right? And so there is a lot to do. And if you want to think about space complexity of proving tautologies, nothing like proof systems, right? And so the notion of short proofs, proof complexity, these are all really beautiful questions in there. Hilbert systems are not very, very nice to do this in. They're hugely challenging. And well, okay. So let me get on with things. This is a side remark to point out that there are very interesting research questions as well. It's not just some plaything that we are doing here. Well, it is. It's some fun stuff. Okay. So I want to move to another proof system, what is called natural deduction. And the reason is there a more structured way to do proofs? I mean, the way we went about it, as I said, a lot of ingenuity is involved, some creativity, which is very nice. But this is not really mechanizable if this is the way you do. But then Hilbert's system, and remember that the entire argument comes from Hilbert's way of thinking, which is that the logical consequence relation is infinitary in nature, right? Because you're quantifying over all possible models, and then you are saying if every model satisfies all the things on the left-hand side, that model, take any model, it satisfies all the things on the left-hand side. And then Hilbert's idea was to replace it by a finitary relation. There is a proof of alpha from gamma. And what you are really interested in, the Hilbert way of thinking, is to show that there exists a proof. Writing the proof, who cares? Maybe a machine will do. But unfortunately, from this system, it's very difficult for the machine to do it as well, right? So are there other ways by which, well, not just for machines, for us also, if I actually want to do proofs, is there some guided way of doing that, right? And this is something that, after all, this is what logicians, people talking about logic, doing reasoning, have been thinking of for centuries. Okay? So this is a very old topic, in fact. And what you would like to do is to look at the formula you want to prove. And, remember the formula is a tree, right? Now, formula is a tree, then what does the root node contain? Well, it's a propositional formula. There are no quantifiers here. So it's going to have some connector, right? So look at, and that's for instance, it's an AND formula. And then 2 subterms, implication. Now, by the way, I didn't write it. The other thing is that whoever wants to write everything in terms of implication, I mean, have you ever thought about alpha and beta as negation of alpha implies not beta? Because it's true. But that's horrible. I mean, is that how you think? No, of course you don't, right? Or alpha or beta as not alpha implies beta, not alpha implies beta, or not beta implies alpha. You don't think in these terms at all. Okay, the Hilbert style system is to do metamathematics. It's very important to do proofs of the kind of completeness arguments that we did, right? Showing that if this is a consequence, there exists a proof. It's not about actually doing things, right? So one thing that you don't actually want to do when you do reasoning is to translate it all into some implication or whatever, right? You want to deal with conjunctions, disjunctions, negation, implication, the words, and actually reason with formulas as they are. And then, as I said, for instance, if you take the challenge that every tautology is derivative, right? You want to prove that. Forget about gamma and all, right? I'm not interested in theories. I'm not interested in whatever fancy theory that you've got. I'm really interested in Boolean formulas, tautology. That's all we are talking about. We'll get to quantifiers later. Then, for every formula, you've got the tree representation of the formula. The root node is labeled with a connector, and let that decide. For instance, if it's a conjunction, well, it's obvious. I must prove whatever is the formula to the left subtree, prove whatever is the formula in the right subtree, I'm done. If it's a disjunction, I make a choice. I try out the left subtree. If it works, okay. Otherwise, I try. I mean, that's the kind if I go from left to right. You can go whatever. Right? Now, there are various ways of going about it and this is the idea of structure. And the other thing is, make assumptions as and when you need, but get rid of them using implications, right? This is something we do in math all along. Assume alpha, go ahead and prove beta, then you have established alpha implies beta, right? And then use alpha implies beta wherever you want. It's a free thing to use, right? This kind of heuristics you can make use of. And this is the spirit of so-called natural deduction proofs. Okay? So natural deduction proof system is, as I said, it was formalized in the early 20th century, but something that has been around for a very, very long time. Almost all people doing formal reasoning who have been talking about proof have some form of natural deduction. But what we are talking about is a very particular system. And even that, I'm going to take some liberties and do some things. You will find in the literature different forms of natural deduction. But the idea is that it's intuitive. So the natural deduction system that I'm going to present has only one axiom. This is the other end of the Hilbert system. In Hilbert system, I said only one inference rule, write down lots of axioms. What is the problem with that? Well, and as I said, as minimal as possible. We'll discuss that later. But we had three axioms. Now, we are going to have only one axiom. And the axiom is alpha implies alpha. Now, it's kind of criminal that a proof of alpha implies alpha should take us so much work, right? We started today's thing with that, right? That seems ridiculous. So here is one healthy way of going about it, to say that's an axiom. And in fact, that's the only axiom, right? Nothing else. And then, for every construct we have got, in this case we have got connectors, Boolean connectors, we have exactly two rules. So, the structure of a natural deduction system is fixed. The moment you decide your syntax of the logic, right? The natural deduction system will have, how many rules will it have? Well, whatever number of connectives you've got, and twice that many. That's it. So it's as abstract as that. So this is really all about structure, entirely about how your language is structured, proof is structured. So you have one introduction rule and one elimination rule. What is the idea of an introduction rule and an elimination rule? Maybe I should write something. Yeah. Okay. So the deal is, you know how bad I am at it. Yeah. So your inference rule is always something below the line, right? here is your conclusion, gamma, and your rule is something like this. Yeah. Now, what is the idea of a proof? I want to derive gamma. I should have derived alpha. Should have derived all this. Think of a proof as a tree, right? I'm going to go about it in a goal-directed fashion. And what am I trying to derive? Gamma. Read the rule always backwards. Right? To derive gamma, I should have derived alpha 1. But the derivation of alpha 1 is a tree again, right? That's why. So this is the way to think about any rule. So the introduction rule, if I want to talk about implication introduction, or let me write conjunction, right? Conjunction introduction, I must have conjunction below, right? And if I have conjunction elimination, I must have conjunction above. Is the idea clear? The idea of an introduction rule says, how do I introduce the connector? Now, if I want to derive alpha and beta, what should you have derived before? Can somebody tell me? Yes, Gayatri?
Alpha and beta.
Yeah, that's it. If you have already derived alpha as well as beta, then you can derive alpha and beta. Can you think of anything more natural than saying this? What about conjunction elimination? If I have already derived alpha and beta, what can I get out of it? Yeah? Kamalika? What am I getting out of it? I want to eliminate the conjunction, right? If I eliminate the conjunction, what is left?
Alpha and beta both.
Both.
Yeah.
Don't use and here because this is conjunction elimination. 1 from alpha and beta. I can derive beta. This is conjunction elimination. 2. And this is it. So for conjunction, there is 1 introduction rule and 2 elimination rules. And as I said, this is the most natural thing you can think of. This is what the semantics tells you. If you have already derived, so if you have already have a proof of alpha, and if you have a proof of beta, you have a proof of alpha and beta, right? Remember, this is really how trees grow from bottom up, right? Computer scientists are, poisoned by thinking tree grows downwards, right? So if I want to have a proof of alpha and beta, you have a tree whose root node is alpha and beta, 2 subtrees, 1 for a proof of alpha, 1 for a proof of beta. On the other hand, if for whatever reason you are given alpha and beta, you can always knock off one of them and use the component formulas. So this is the idea of for conjunction. Okay, now what about disjunction? What will be disjunction introduction? Disjunction elimination. Yeah. Now, disjunction introduction, what should be below the line? After all, it's introduction. If I'm introducing it, yes, Ananya? What should I have
Alpha
here?
or beta.
Alpha or beta. That's why I said it's so structured, there is very little choice. Now, if I want to derive alpha or beta, what should I have derived before? I want to say alpha or beta. Yes?
Either alpha or beta.
One of the two, right? So, for instance, this. So, I have 2 introduction rules now. This is exactly duality, right? For conjunction, I had one introduction rule, two elimination rules. Therefore, for disjunction, I have two introduction rules and one elimination. The structure also shows the duality of conjunction and disjunction. So this is the OR introduction rule. Okay. Now, what about OR elimination? That means alpha or beta is above the line. Now, from this, when can I derive alpha?
We also have not beta.
Sorry?
When we also have not beta.
Not beta. Well, then you should have two elimination rules. One like this. So we call it R elimination 2. But this goes against the principle I said, right? Because for conjunction, I had one introduction and two elimination rules. For disjunction, therefore it makes sense to have two introduction rules and one elimination rule, but you're giving me two. And also, where did negation come from? Suddenly negation is coming in. So this rule is kind of ugly, right? I mean, it's fine. It's sound. It's okay to. That's why I said there are all kinds of natural deduction rules. Now, but many logicians would not accept a rule like this because this is. So this is something that it's too ugly. So for this instead, what we do is to. Oops, do what computer scientists do. Right? When you reason about if then else, how do you reason about if then else? Right? I write a program, I say if condition holds, then S1, else S2. Now what you say is that, well, I don't know, right? Whether the condition is going to hold or not, right? In both cases, I do case analysis. In both cases, I say that, okay, if the program goes through S1 or S2, at the end, no matter what happens, this is the final condition that is established, right? This is how you reason when you work with your programs. Now, this is something based on a very interesting logical principle. Oh, it's now, what should I do? Drop. I forgot now. What should I select here? Text, right?
Draw a line. Probably there is line or something option
I have
there.
no
Draw a
idea.
line.
Okay, one of these things. Draw.
There's a S type of sweeping S. I think
This one?
it's click on it.
Yeah. Okay. Thanks. Yeah. So this does work. Yeah. Suppose I have got alpha or beta, and from alpha I can do some proof, and I can get a gamma, and from beta I can get a proof and get a gamma. From this I can derive gamma. I've eliminated the OR. How did I eliminate the OR? I did case analysis. This says there are only two cases, alpha as well as beta. From alpha, I have managed to derive gamma. From beta, I have managed to derive gamma. So that means in all possible cases, gamma holds, and therefore gamma holds. Right? This is exactly what we call case analysis. This is a disjunction elimination rule, and this is very popular among logicians. Now, I am not selling this rule. Huh? You can take Aditya's rule and say if alpha or beta, and if you approve not beta, that's okay. Any of these is okay. But the main point about doing natural deduction systems is that worry about the structure of your proofs, right? So, and this rule is something that logicians like. Most people who work on, the computer science types, who try to automate proofs, do automated deduction, machine proofs, don't like this very much. Why? Where did the gamma come from? Come on. We are talking about alpha and beta, and now suddenly you are pulling out a gamma. Now, how is the machine going to ever able to guess a gamma that is needed? These are all, I'm not going to, as I said, sell this system or that system to you. I'm going to present a system, and the main point for our course here is to see that this kind of proof system is possible, and you can carry out proofs. And what is very nice is that you will see that unlike the earlier proofs we did, the proofs flow very naturally in the system, right? There are very, once you decide the rules, it really carries you through as to how the proof should go. So I mainly want only that experience. But, there are extremely interesting questions here to take up, but that's a separate thing. So this is for conjunction, disjunction. What about implication? Yeah. What about implication? So again, we need one for implication introduction, and we need one for implication elimination. Yeah. Okay. Sorry about my lines. Yeah. What should I have? Now here, alpha implies beta is below the line. That's for sure. And here, alpha implies beta is above the line. Now, implication elimination is something you have seen all the time. What is that? We have been calling it modus ponens. This is implication elimination, right? If you've got alpha implies beta and you've got alpha, you can derive beta. That's exactly implication elimination. What about implication introduction? Well, suppose you make an assumption alpha, let me write it as a bracket, and you go on doing proofs and you have actually managed to prove it. Then you have proved alpha implies beta. That is, making alpha as an assumption, if you have proved beta. No, this is an assumption you have made. By this process, you have actually discharged the assumption. This is the idea of natural deduction. I think I already mentioned that that's the spirit of natural deduction. And we will see that. I mean, this is just a way of writing the proof. It looks slightly different from the way we were writing rules in the Hilbert system, but intuitively it's clear what we are doing. What about negation? How do you introduce negation, and how do you eliminate negation? Have we seen something like negation elimination so far?
Sir, will there be two introduction rules for implication?
No, for implication, one is enough. I mean, this is a rule that I suggested. Oh, you're saying by duality. But duality is only between conjunction and disjunction, right? Implication is not dual to any of them.
What if we have not alpha above?
Yeah, I mean, you could have. But negation is a separate connective. Remember, the philosophy is one introduction rule and one elimination rule for each construct. That you can have components A, B, and so on, right? But it should involve only that construct, right? You don't want two constructs in one rule. If you're talking about using for implication or for disjunction, you are using negation, then there are two constructs involved, right? I don't want to use two constructs. As I said, you can have, it's not that, but the point is you want to be as structured as possible in the design of the system. Okay, for negation introduction, negation elimination, any idea? Well, one way we have seen for negation, no, this is one way you can try to do negation introduction. Which to call elimination, which to call introduction is a lot of, fight between people on this. I'll let you try whatever you want on this. For instance, this is what I would call negation introduction. Instead of bottom, you can put any beta. I mean, if you prefer that, you choose arbitrary formula. From a contradiction view, now where is negation introduction? It's actually bottom introduction, right? And what about this? So it's really, the way I'm writing it is bottom introduction and bottom elimination. And this is the form we have seen so far. From not alpha, I go on doing things and I derive a contradiction. Then I eliminate. Right? This is the reduction observed that we have. Now, some people will use this for negation and elimination, and for negation introduction, from alpha I get bottom, then this is negation. Yeah. As I said, lots of variations are there. We can choose some particular combination and go ahead. They are all sound, and almost most of these are complete as well. Okay, so that's pretty much it for the, and that's it, huh? Because, well, by implication, it's also as ridiculously simple as this. Yeah, there are no, yeah. So let me get back to my screen and show you these rules. So we have these. So first, conjunction. Conjunction introduction is that if you have derived alpha and if you have derived beta, you have derived alpha and beta. Conjunction elimination, if you have got alpha 0 and alpha 1, you are allowed to derive alpha 0, you are allowed to derive alpha 1. Implication, making assumptions and discharging them is central to the system. So this is a notation you better get used to. I make an assumption, put a bracket or put a star, doesn't matter. Something saying that this assumption is what is being discharged here, right? This is implication introduction, discharging the assumption now. And implication elimination is simply modus ponens. And that's that. And then disjunction. And as I said, if you have derived alpha or beta, assuming alpha you derive delta, assuming beta you derive delta, then from that. Disjunction introduction is from alpha 0, you can derive alpha 0 or alpha 1. From alpha 1, you can derive that leaves negation. As I said, I have used this for this is really bottom introduction and bottom elimination, as I call it. And well, as I said, in the literature, you will find variants of this, and all of these are reasonable. That's it. So, what is the natural reduction system? It's got one axiom: alpha implies alpha. Implication, conjunction, disjunction, negation. For all of them, we have talked about the introduction and elimination rules. Notion of proof is exactly as before, right? And except that I'm writing them vertically here. That should not really affect you that much. And you can do proofs. And now we can show that, how do you prove that the natural reduction system is complete? Well, we can show that the axioms of H are derived as theorems. Right? Note that modus ponens is already a rule in the system. So the axioms are derivable. The original rule is derivable. Therefore, whenever there is a natural reduction proof, there is a Hilbert-style proof. And whenever there is a Hilbert, I'm sorry, the other way. This is what I meant. Whenever there is a Hilbert proof, right? Since those axioms are derivable, there is also a natural reduction proof. Right? And now you can use the completeness of the system originally, and that's it. And proofs are a lot easier in natural reduction, and they can be easily automated as well. Now, look at this one. This is extremely useful because the Hilbert axioms are all in the implicational form, right? Suppose you want to derive the first axiom, alpha implies beta implies alpha, right? How do you do a proof in the natural deduction system? We are supposed to derive alpha implies beta implies alpha. But for that, you must make an assumption alpha and prove beta implies alpha. How do you prove beta implies alpha? You must make an assumption beta and derive alpha. But you already got alpha and you just have to derive alpha. Alpha implies alpha is an axiom. So put that in, you'll get it. So it's completely straightforward. Mainly because the Hilbert system is exactly in the implication. Please check it out, go over it. The one with the alpha distributivity looks horrible. But if you write it as a tree and devise it as subtrees and go on using the implication, introduction, and elimination, you will find that this is all you need to do. Right? And the only things you will keep going to the axioms as alpha implies alpha, beta implies beta, gamma implies gamma, and from that you. What about the third one? The third one, the form that I have chosen is to actually use array. Right? As I said, we have bottom, and the rule for bottom is also clear. So I want to show the array axiom. Start with not alpha. I've got not beta, beta, right? From that you get a contradiction. You use the bottom and do the elimination. So all the Hilbert axioms are derivable. And as I said, so if I take any proof in the Hilbert system, right, I can rewrite it as a proof in the natural reduction system. So this is clear. And now, what about all the things in the natural reduction system? We have to show that they are sound in the Hilbert system. We need to do that, right? For completeness, we have to do that. Now, but this is easy. We just have to prove that, from alpha, not alpha, you can get any formula beta in the Hilbert system, right? So we have to show that all these are derived rules in the Hilbert system, right? And as I said, this is simply a formalization of array. This is something that we have got, and all the other rules, right? This is all derivable in the Hilbert system, right? Now, the painful part is that in the Hilbert system, everything is in implicational form. So I have to rewrite this as not alpha not implies alpha 1. Not alpha 1 implies alpha. Right? And I have to show that I can do that. But I assure you that these are all very straightforward. So all these now can be shown as derived rules in the Hilbert system. And basically this means that from this assumption, you can derive this in the Hilbert system, if you've got all these. Once you do that, the completeness proof is done. Yeah. So once you show all the rules are derivable, that means take any proof, wherever you apply the natural deduction rules, you can replace by the corresponding segment of the Hilbert. And therefore you get it. Now, the main point is that proofs are a lot easier in natural deduction and they can be easily automated. For somebody who's interested in programming and tries to program things, for Boolean formulas, I would say it's a very good exercise to take up. Choose your favorite natural deduction system. Like I said, I've already discussed some examples. I've presented a system, but as I said, you can take variants as you like. And now, then take any tautology, and actually, your program should take a formula. And if it's a tautology, we don't care if it's not a tautology, it can do whatever it wants. But for a tautology, it should actually construct a proof using it. It's actually something that's eminently doable, and I would recommend that you try it. Okay, thank you. Sorry for taking a little longer. But let me say that concluding remark is that you must try to, you must dirty your hands, do some proofs in the Hilbert system, do some proofs in the natural reduction. I will send you some exercises, and only when you are comfortable with them, because this business of doing proofs, listening to somebody, discuss proofs is never a good idea. You have to dirty your hands and try out different formulas, then only you. Okay.